This video is covering waves. A wave is any disturbance that transmits energy through matter or space. Energy is always carried away from the source. The material through which the wave travels does not move with the wave, but its particles vibrate in simple harmonic motion. So in this illustration, you can see that even though the wave is moving from left to right, the particle is moving up and down. Waves can be classified in two ways. One way is on how it can travel and what it can travel through. The two categories are mechanical waves and electromagnetic waves. Electromagnetic waves can transmit their energy through a vacuum. They can also travel through a medium, but it is not required. Mechanical waves must have a medium. They are not capable of traveling through a vacuum. A medium is just what we call the matter through which a wave can travel. This matter can be solid, liquid, or gas. Waves can also be classified based on their movement. There are three: transverse, longitudinal, and surface waves. Transverse waves, particles in the medium move perpendicular to the direction of the wave. This is similar to the wave from the first few slides. Here we can see the wave is traveling from left to right, and the particles are moving up and down. A crest is the highest point on a transverse wave, and a trough is the lowest point. Longitudinal waves have particles in the medium that move parallel to the direction of the wave. So here we can see the particles themselves are moving left to right, just like our wave is moving from left to right. The two parts to a longitudinal wave is the compression. This is where particles are the closest together or the densest. And then we have a rarefaction, and this is where the particles are farthest apart. So here you can see again the compression and a rarefaction. Lastly, we have the surface waves, and these waves occur at or near the boundary of two media. They're also a combination of both a transverse and longitudinal wave. And because of this, they make particles in the medium move in a circular motion. So here is an example of that. So here we can see in our water waves, and think about it, water waves occur at the surface of the liquid water and the air. And we can see the particles there moving in a nice circular motion. Seismic waves are also examples of surface waves. And we can see, again, those blue dots representing our particles are moving in a circular motion. Electromagnetic waves travel as transverse waves only. Mechanical waves, however, though, can travel as transverse, longitudinal, or surface waves. Let's talk about some properties of waves. They have an amplitude. This tells us the maximum distance the wave vibrates from its rest position. The wavelength, which is symbolized by the lambda, and that's just the distance between any two adjacent points on a wave. Usually those points will be crests or compressions, but it could be any 2 points that are adjacent to one another. Next, we have the frequency, which is symbolized by lowercase f. This is the number of waves produced in a given amount of time. And we have the wave speed or velocity. Now let's talk about some properties of waves. Now let's talk about some properties of waves. We have the amplitude. This is the maximum distance the wave vibrates from its rest position. It is normally measured in meters. Next, we have the wavelength, which is symbolized by the lambda. This is the distance between any two adjacent crests or compressions, or really it can be the distance between any two adjacent points. It doesn't necessarily have to be crest or compressions, but normally it's between crest and compressions. And it's also measured in meters. Next, we have the frequency. This is the number of waves produced in a given amount of time. It is measured in hertz, named after a famous scientist who was credited with discovering radio waves. Then we have now let's talk about some properties of waves. We've got the amplitude, which is the maximum distance the wave vibrates from its rest position. It is measured in meters. Next, we have the wavelength, which is symbolized by the lambda. This is the distance between any two adjacent points on a wave. Most likely those points will be crests or compressions. This is also measured in meters. Next, we have the frequency, which is symbolized by a lowercase f. This is the number of waves produced in a given amount of time. It is measured in hertz. Hertz was a famous scientist who discovered radio waves. Next, we have the period, which is symbolized by a capital T. This is the time taken for one wave or cycle or vibration. So these are all synonyms of one another. So wave, cycle, or vibration, they really are the same thing. This is measured in seconds. And the last property we're going to talk about is wave speed or velocity. This is the rate at which the wave travels. It is measured in meters per second. Next, let's just take a look very briefly of a transverse wave so that we can actually see what some of these things mean. So as you recall, the crest is the highest point on a transverse wave. A trough is the lowest point. The amplitude is from rest to crest or from rest to trough. That means the maximum distance the wave moves from its rest position. Then here we see the wavelength from crest to crest. But again, this distance is the same as it would be from trough to trough or from the start of the cycle to the end of the cycle. All of those should be the same length. Next, we have the example of our longitudinal wave. We have the compression and we have a rarefaction. Again, the compression is where the particles are the densest. The rarefaction is where the particles are farthest apart. And then here we see the wavelength. Again, it's between two compressions. It is hard to show the amplitude in just one two-dimensional picture on a longitudinal wave. It's easier to hear it, but you're going to be looking at a simulation soon that's going to help you understand that. A wave pulse is really a single disturbance. So we hear on our slinky, it's just one disturbance. All right, then we call a series of those a wave train. So this is a continuous wave. So it's a series of pulses at regular intervals. So here we see one on a slinky, and then here we see an example of one. Okay, so you'll hear both of those terms referred throughout this unit. This is the conclusion of the waves video.